I should think. But there's a peak here at right about 430 centigrade. And we did this 4 times, as reported in the paper. And each time, the ignition point is close to this temperature. Now, the red curve, this is interesting. This is known nanothermite, published by Livermore, not classified information. And this is the result that they got. We followed their experimental conditions so we could compare apples with apples. Which is to say, we ran then just as they did in air and at 10 degrees centigrade per minute heating. This nice narrow peak that they got indicates the thermite reaction. We have an even narrower peak. The narrower the peak, the faster the reaction has occurred. And furthermore, if you integrate this, I think these are close to the same energy, if I remember correctly. But other peaks that we got with the red-gray chips are larger. There's one about a factor of 2 larger than the theoretical maximum for thermite, ordinary thermite. It's interesting. It would suggest to us that the organic material in these chips is also itself a very energetic material. That needs to be sorted out. But the energy has been measured. You integrate the area under the curve to get the kilojoules per gram. For those of you that want to do that, it's not too hard. Okay. Point is, this is a very narrow exotherm, and it's at a low temperature. Now, what happens if you do ordinary thermite? Shown here in this paper by Gash et al. Again, Livermore. This is ordinary thermite ignites around 900 centigrade. Nanothermite ignites, in their case, around, I should look here, I'm just trying to remember, about 550. Again, the finer the thermite, there could be other factors, the lower the temperature of ignition. This is another big difference between conventional thermite, which ignites above 800 centigrade, and nanothermite, which ignites typically at an appreciably lower temperature, just as we see in the red-gray chips, the blue curve. Lower temperature, narrow exotherm, and again, narrow exotherm. And by comparison, under the same conditions as best we could from Tillotson. Jeff contacted Tillotson. That's this paper, Tillotson et al., the red curve, and discussed the conditions so we could match those as best we could. A lot of energy, folks. Narrow exotherm, that's very important because it means a very rapid reaction. Now, this is, we'll review briefly. This is like no paint you've ever seen, this red material. Ordinary paint dissolves in MEK. This material does not, even after 55 hours with agitation. Resistivity is lower than we found published for paints. That's some data, it's not maybe the strongest, but there's some additional data. We did that measurement attracted by a magnet, which is kind of unusual. I don't know of any paint that does that, but here are the crucial data then, along with the lack of dissolving. Carbon, silicon, oxygen, iron, and elemental aluminum found in the red material. That would be interesting to find that combination in a paint without zinc, magnesium, titanium, or chromium. Yeah. Interested to see any paint that, as I pointed out, the primer paint used on the steel in the World Trade Center did have zinc, so that rules that out for this material. The faceted grains is also quite uniform, and the aluminum in plate-like structures, 40 nanometers thick. This is actually looking like a fairly highly engineered material, but if you think about all these features. Furthermore, the narrowness of the peak in the DSC test, ignition at low temperature. By the way, we did ignite paint. Jeff ignited some paint in the DSC. The exotherm, it does burn, and it's just a broad exotherm. You know, this is narrow. You saw the blue peak. The paint is very broad. I didn't have it available, unfortunately, to travel, but I need to get that from Jeff or something. But it's very broad. I've seen it. It's about 10 times broader as I look at that with Jeff, too. than the exotherm that we see with this red material. And of course, the production of these spheres. Oh yeah, the uniformity, I think, is a very important point. Applying an engineered material. We did controls. We looked at the dust from the collapse of, this is in the paper, the Stardust Resort Casino in Las Vegas, which was demolished using conventional explosives, 2007. The Key Bank, also demolished with conventional explosives, and Danny Farnsworth and I looked, we found no red-grade chips whatsoever. Now, you can see in the paper, a small amount, what was it, about 5 grams had some 60 of these, you see, and to find none in larger quantities than in these controls is significant. In other words, you can't just get it by bringing a building down, even though it's got steel and aluminum in it. You don't get this highly engineered structure with carbon, mind you, in there. This is from an April 2001 conference, again before 9/11. They say, it's interesting, there was a session discussing this. Okay, work on this field is roughly 10 years old, so that would put you back to 1991, well before 9/11, 2001, but well after the construction of the buildings. Okay, so it's not like they would have used this because this is well after the buildings were constructed. In 1970s, wasn't it, Jim? Sorry.
Oh, yeah.
1970s.
Early 70s, yeah.
Early 70s, the buildings were built. So this is more recent than that by decades. Unique properties of nanomaterials that have potential to be used in energetic formulations for advanced explosives. Hold on, I got some more really interesting stuff in this AMTIAC report. Department of Defense information talking about this. Here's a figure out of that report, applications of this material. And they talk about munitions. They talk about thermobaric uses here. Thermobaric, can you read that? Thermobaric. And then they talk about a shaped charge using this nanocomposite. Right? A shaped charge you can build with this. That's what is required, folks, to cut through steel. This is an example of a conventional linear charge on steel. When you set that off, which can be done with a radio signal, then remotely. You don't have to string a bunch of cables or something to do this. You can set it up with a radio signal. Small radio receiver picks that up and bam, explodes its way through steel. That's the nature of shaped charges. Here's a chip found by Kevin Ryan in his sample, obtained independently. And you notice this is an interesting one because it has globules. It looks like this has reacted in the center of this chip. It's very unusual, but I just wanted to show you that he found this, and this shows it looks like a partial reaction. One of the thoughts that co-author Frank Legge had is that the thin chips survived. There could have been much thicker material present, but it reacted, and then the thin chips could have been quenched for one reason or another and survived with only partial reaction, as you see here. Okay, how do you make this stuff? This is again from the AMTIAC publication, this report. This shows synthesizing nanoscale aluminum for these applications. This is at a naval facility, Indian Head. It's very complicated. It's not trivial to make large quantities of this nanoscale aluminum. This was done in 1999. This plant for producing large-scale quantities of this. I'm not saying it's the only place in the world, but one of the professors involved in this development at this naval facility said it was the only facility. I mean, it was the first, is the way he put it. So